Radio people, 2018, question 1, higher level. So, Boyne Bridge uses steel cables. Outline one method to protect the cables from corrosion. Okay, well, you could do painting or galvanizing. Now, basic, I'll go with the galvanizing, but painting would be fine too. So that is dipping steel into molten zinc, melted zinc, so it gets a coating on the surface. This stops the steel from rusting or corroding. That'll do. Now the second one there, then, describe with the aid of a diagram the principles of a tensile test. Okay, the principles. So what I'm going to do, I hope, is I'm going to draw a base for a machine here, maybe. So there's our base for a machine, and we'll just put a frame then coming up from these. So let's just put a frame like this. And what we want to do then is we'll just put a kind of a ram up here. And it's important now to put the same thing coming down from above. But they need to be right in line, and what we'll do there then is just put on a test piece here, and I think we're going to put the test piece in broken. So we'll say we're after the test. I'm going to colour in our test piece. So that's like a dumbbell from weights. So there's our dumbbell when it's broken. Here's our machine. So basically it gets attached or clamped on up here on top, and this can get pulled down so that it gets torn apart. So I'll just put an arrow in there to say that this can get pulled down. We'll just put maybe a couple of buttons on this here to make it look all professional, and maybe a readout here. And some numbers. So the question said, with the aid of a diagram, the principles of tensile testing. Okay, so the test piece is clamped and I will say pulled, stretched, or you could say it has tensile force applied to it until it breaks. And the amount of force it takes to break is recorded, and also how much it stretches as the force increases. Okay, so that's basically the principle, and I suppose the last thing there I will put in maybe is that there's two types. There's a round one that looks like a dumbbell and there's another one that looks like more rectangular on top. It's more like a doggy bone. Like that. Okay, I probably drew it a small bit too angled there now, but it'll do. So just stick the colours on this again because it just links to up here where it's broken. So like that's a nice simple sketch now of machine and the samples. So they're test samples. So it's a describe at the end of a diagram the principles. So piece is clamped, pulled apart, and you measure the force it took to break it and how much it stretched before it broke. So that's loads. Okay, so next then we have, you were given those graphs there. So like I'm not going to get into them there now. Just going to draw B here. So there's something like this. You had one this is the curve for mild steel, because it's very recognizable, and this one is pretty similar, and I'm guessing that that's stainless. And the last one here then is the one that you'd see there then is often used to compare, and I would say that's copper or aluminium. Now I might as well read the question after doing all that. So state which of these. Oh yeah, copper, low carbon or stainless. Okay, alright. So copper, so it is copper, right? But aluminium is very similar. I'll just write similar. So state which of the three is which. Okay, so that's alright. And compare A to C with reference to the shape and the properties. Okay, so A, I'm kind of squishing it in here now, and I don't like doing that, but okay, A has a good elastic region. So that's here. Our elastic region is here. I'll just underline it in blue. That's our elastic region. And then it yields. So it gives there. And then it has good plastic, or a lot of good, will I say good, or a lot of plastic deformation, which means it stretches a lot before breaking. Okay, so that's A, and I wanted to compare it to C. And the last thing I'll say there is just coming across from this here. on the table. I'll just get a reading there of that. I think it's around 320, roughly anyway, and that would be newtons. It had a ultimate tensile strength of 320 newtons, so it was strong, stronger than copper. Because if I come across some copper there, just having a look at the thing here again, copper was about 150 newtons, so it was much stronger, like twice as strong. Now, as usual, I wedged that in there and regret it straight away. Like, better off to have gone to a new page there. But anyway, so compare the shape of them and the properties. Okay, so the properties. Okay, so A was stronger, a long elastic region and a long plastic region, and probably then ductile fracture. So B then, which is the copper, so that was the steel. So the copper there then would have less of less elastic region and long plastic deformation region and ductile fracture as well, slash cup and cone fracture. So so compare them with reference to each other. So I don't know, you know, it only takes a second to draw your cup and cone fracture. I mean, why not? Like, just draw the color on that there. Like, for the sake of 10 seconds there, you know, you're showing that you understand this. So ductile slash cup and cone fracture. So that is that part. Now number 3 then said determine the ultimate tensile strength for metal B. Now I did that in the back. I think I said it was 320. Now if you had it drawn 320, okay, so I'm going to say 320 newtons per millimeter squared. So it's something close to that anyway. Alright, so C there then. So it says bronze alloys are used for propellers as part of quality procedures. The bronze propeller is non-destructively tested. So what's an economic benefit and a safety benefit for using them? Well, so the economic is pretty obvious. You can't have destructive tests on every part because you have to destroy it to test it. So otherwise you'd make nothing. So the economic is that you can test the part without damaging and then sell it. So that's faster and more profitable. So as I said, like, you cannot do destructive testing to everything because otherwise there is zero production. So that's our economic one. And then the safety one then is you check for, let's say, internal flaws and external surface cracks, and it's safer if it passes the test. So it's said there to outline one economic benefit and a safety benefit. Okay, so it's safer because it's passed the test and economic, so that'll cover that. And then describe a suitable non-destructive test. I examined the propeller for flaws near the surface. Okay, so near the surface. Now, you could get away with probably X-ray testing, but most likely near the surface on a non-ferrous metal, they're probably looking for the magnetic field testing. So I'm going to draw just here a test piece, and we're going to draw then just plus, and that was a plus, this is meant to be a minus. So I want to draw in here now just a copper coil. Okay, now what that does there is when you run a current through this copper coil, that generates a magnetic field, and that magnetic field will penetrate. Okay, so the coil produces a magnetic field that induces currents in the test piece. So let's put in a flaw here now. Let's put in a defect here as well. I might put it in here as in red. So let's say that there's a void here. So that's an air pocket, also called a void defect. So like that's basically inside, underneath the surface, and I'll just say that the void defect will interfere with the current flow in this and show up on the monitor. Thank God for monitors. So let's connect this onto a quick monitor over here. And let's give this a big beep. And we'll just connect that back over to here as well. So, okay, so something like that will do the job fine. I mean, it kind of gets the point across that you've got a coil generating a magnetic field that penetrates the non-ferrous metal, and it'll show up there. So oh yeah guys, I forgot to just put down up here at the top, economic and safety. Okay, so that's eddy current testing. I better write that here. That's okay. So I mean, it's basically a kind of magnetic field, but they're called eddy currents. So the coil causes currents to flow in the non-ferrous, in the bronze casting there. So the void in the induced currents. So there, I should write in here eddy / induced currents, and show up on the monitor. So that's eddy current testing, and yeah, that'll do the job for that. See you later.